So, 3D city models are very useful for a lot of different use cases. Some of them are determining solar potential by seeing if any tall buildings are blocking out a shorter building, urban planning, emergency planning, and just pure visualization. But an issue with creating these complex 3D city models is that it requires a few different data sources and often manual labor that can be both expensive and time-consuming to collect. So what I wanted to do with this project was to automate this with cheap data and open source tools. So, in this space, a 3D building can mean one of many things. So that's what I want to get across here. In the most simple case, you have a rectangular prism, which you see little detail 1.0. And in the most complex case, you have complex roof shapes, extrusions, doors, windows. The more complex you get, the more use cases you can have for it, but it's also the more difficult to obtain. And for this talk, I'm going to be focusing mainly on this upper left area. The standard ways of making 3D city models combines two different data sources. The first of which is called LiDAR data, which is collected by an overhead plane that shoots lasers in multiple different directions and measures the amount of time it takes for the laser beams to get reflected back to the plane. And from this, you have a collection of 3D points that can give you insights into structures of forests, bridges, and buildings. And then once you have this, you can create a 3D mesh out of it and overlay imagery that you would take at multiple different angles around the area that you're interested in. This can produce some really stunning results, but it's not always available in a lot of different regions that you might be interested in. Specifically, it's usually available in like high population zones and certain cities. So, then typically you would need either expert level tools or experts in the subject area to create these 3D cities. I wanted to see an alternative to do it without being a subject matter expert, which is why creating this with machine learning was so attractive, since machine learning can find those patterns and solve those patterns without needing to be a subject matter expert. So let's talk about some of the methods I used. So typically with an image machine learning problem, one of the most common frameworks that you would be using is the convolutional neural net. And the general idea of these is that you have some features that need to be learned that are important for making a prediction. And a convolutional neural net looks at multiple different points in the image and tries to learn these important features. For example, like in this cat image, things that might be important for predicting a cat are like the two eyes, the shaped ears, or the pink nose. So that's one of the things that this model could be learning. For my specific use case, I'm not making an overall prediction for a whole image. I'm making a prediction per pixel. So that kind of problem is called image segmentation. And this is a similar architecture to what before, but it has a second half step. So in the first half, like in the previous slide, the net is learning some general features that are important to making a prediction. And then in the second half, through a series of upsampling along with skip connections that keep context that you learned along the way, it tries to learn a certain amount of features per pixel based on the pixels around it to make a prediction on whether or not a pixel is a part of a certain class. So the output you would see of this when you feed in a cat would be a collection of pixels that get marked as cat and a collection of pixels that get marked not as cat. All right, so this is the actual kind of structure of my problem. So what I feed in is 2D overhead imagery. I feed it into this neural net, and what I want to get out is both the footprints of where the buildings are, and also per pixel the height in meters. So this is kind of like two separate problems. but the problems are pretty similar. A lot of the same features that are used for predicting buildings will also be used for predicting pixel heights. So I put those together into a single network that has two outputs. And this saves training time for one, and it also saves time in deployment if you were scoring over a large scale. All right, so when I was thinking about the type of imagery I would want to use for this project, there are a few parent sources that would be good candidates. The top one is from satellite imagery from Worldview 3. It has the most detailed spectral and spatial information. You get coverage all over the globe, which is great, and the revisit rate is every day, but the cost per square footage is very expensive. The two sources below it are either free or cheap, and they're collected, usually government sponsored. The NIIP is sponsored out by an agricultural agency, and that's collected every 3 years across the whole US, and it's free. So that was a strong candidate that I wanted to talk about in this talk. Sandboard imagery is also a good candidate, but it's only available in certain parts of the US, and my idea was to try to score this on a large scale. So I made models with all three of these, but I'll be reporting the results from NIIP. All right, so to get the ground truth that my model is going to learn from, I have building footprints from a challenge issued by SpaceNet, the challenge was trying to find image footprints from their Worldview 3 imagery. So those were very useful for making that ground truth. And then the pixel height ground truth was a little bit more difficult to derive. An area that I was interested in, Las Vegas, there is LiDAR data that's freely available, but it's very low quality. So then the pixel-wise output that you get out is also low quality. The pixel spacing, or the point spacing of LiDAR point cloud is around 1.7 meters, which means that, and it's quite noisy as well. So the output pixel height you get is a little bit messy, and for every building you kind of just get a blob of high pixels. All right, so this is an example after my machine learning algorithm has been training for a while on how its output compares to the LiDAR height ground truth that I was learning from. So this image kind of shows some of the issues with the LiDAR data, because I want to point a little bit. The bottom right has this large spike of high pixels that got erroneously flagged as being high from the algorithm I used to create this image from the LiDAR data set. That large spike there is actually a ditch below ground that it's flagging as being high above ground. My model's outputs kind of learned to ignore that, so that's great. But what some things that my model didn't do as well is in the top right of this image, you can see a larger building. And although it gets like the whole building in the heights, you can kind of see two smaller blobs in that larger building, because the model is a little bit biased to predict buildings of that shape, since this data set was primarily residential areas. So that could cause an issue if I was ever trying to drive like a roof-shaped estimation from that. But in general, like some of the two-story buildings that you see that are lighter in the middle image get classified as lighter in the right image. And some of the building footprints get messed up if there's obstructions on the roof, like solar panels. All right, so the results of this, scoring this on the entire area of Las Vegas are not perfect, but they are promising enough to show that there is something there that can be learned with NAIP imagery, I think. The results as you go into higher resolutions with Sanborn and Worldview 3, they're definitely higher, but I think NAIP still is a strong candidate for scoring on a large scale. So it does the best on when the number of stories of the building is less than the single story. So this is like less than 2-story structures, either like coverings of cars or whatever else is very short. And it gets those right around like, I don't know, around 90% of the time. And where it messes up the most is when the true height of a building is around 1 story tall. it is incredibly biased to predict two-story buildings. So that's an issue where maybe some kind of smarter sampling could help it differentiate a bit between the shorter buildings and the larger buildings. Two-story buildings, it does okay, a little bit of spread there, and the three-story buildings does about as well as the two-story buildings. So if you apply this to certain images, this is kind of the output that you would see. This is overlaid on top of Google imagery. In the bottom left, you can kind of see a three-story apartment building. Its register is kind of high. And then over to the right of it, you kind of see carports that are registered as lower, so that's promising. But over to the right where you get to the residential buildings, there's a lot of error that you can see in this. For starters, couple of the images get registered to be about as high as the carport, and that's typically when they're around the same color as carports. So that's something that would need to be corrected for. And overall, most of the buildings get labeled as 2 stories, which is great, and a few as 1 story. So the footprints performs pretty well, but the heights are where the model starts to struggle. And with NAIP imagery, this is a little bit more expected because with higher resolution imagery, you can kind of see shadows alongside the building, and shadows could be a strong indicator of how tall a building is based on the length of the shadows. NAIP is too low resolution really to see that. All right, so with the NAIP imagery, the shapes of the building is great, but the extruded heights definitely could use some room for improvement. As far as the roof shape, which is another task that I wanted to at least look at in this problem, I feel like the Stamboard imagery, like the higher resolution, around 30 centimeter imagery, has the capability of solving this problem. There are several buildings where it was able to do that, but the height data that I had wasn't quite good enough to pick up the nuances of a roof shape. So even if there is information spectrally to see that, it wouldn't be able to learn that from the ground truth information that I have available. All right. And some acknowledgements I want to throw out is from the SpaceMet Challenge. The footprints that they provided were very useful for training a model, and also from the solution written by Kohei Asaki, who introduced me to the problem to image segmentation in general and to how to apply neural nets to solve an image segmentation problem. All right, thank you.